Hello and welcome. My name is William, and today we're going to look at some source code for the Eulerian Path algorithm. This video follows off my last videos explaining the Eulerian Path algorithm itself, so I highly recommend you watch those videos before watching this one. There should be a link to that in the description below. Also, all the source code I'm going to present today is available on GitHub at github.com/williamfizet/algorithms. Also a link to that in the description. So without further ado, let's dive right in. Awesome, here we are in the source code for the Eulerian Path algorithm. This code works by first instantiating this Eulerian Path solver class and then calling a method to fetch the Eulerian Path itself, should it exist. Let's begin by taking a look at the class constructor. In the constructor, what you do is you pass in a directed graph to the algorithm as input, and then the constructor verifies that you actually passed in a graph that's not null, and it also initializes a few variables, including n, the number of nodes in the graph, and the path linked list. Before we go too far, let's have a look at some of the instance variables for this class. We already talked about n, the number of nodes in the graph. Next, we have edge count, which we will compute dynamically from the input graph, followed by in and out, which are integer arrays to track the in and out degree of each node. Then we have path, which is the Eulerian path solution, as well as a reference to the input graph. So once you create an instance of this class, there's only one public method, and that's getEulerianPath, which does exactly what it says. It'll return to you an integer path consisting of the nodes you need to traverse to get a valid Eulerian path, or null if no path exists. So there's a few things the getEulerianPath does, which we'll cover step by step. The first thing in the getEulerianPath method is the setup method. So let's have a look at that first. All the setup method does is loop through all the edges and increment the in and out array degrees, as well as compute the number of edges in the graph, which is being tracked by the edge count variable. Back to the getEulerianPath method, the next thing is to check if the edge count is 0 and return null if we don't have any edges to work with. Following this, I call the graphHasEulerianPath method, which verifies that our graph actually has an Eulerian path because most graphs don't. The graphHasEulerianPath method is also fairly simple. What we want to do is make sure that no node has too many outgoing edges or too many incoming edges, as well as ensure that there's the correct amount of start and end nodes for an Eulerian path to exist. The variables, start nodes and end nodes, keep track of how many nodes have either exactly one extra outgoing edge or one extra incoming edge. For an Eulerian path to exist, there has to be at most one start and end node. So when we're inside the for loop, we have three conditions. The first is to identify if the current node has too many incoming or outgoing edges, which mathematically means that the difference between the in and out degree or vice versa is greater than 1. In this case, return false because the path is impossible. There will be no Eulerian path in such an event. The other conditions we care about are whether the current node might be a start node or an end node. And if it is, then we increment the start node and end node counters respectively. The last step is to actually check that we have the correct number of start nodes and end nodes and return the Boolean value. Returning back to the getEulerianPath method, the next thing in the algorithm is to actually find the Eulerian path now that we know one exists. To do this, we find a valid starting node and feed that as the first node to the depth first search method. So let's have a look at both of those. We don't want to start our Eulerian path anywhere, as we saw in the first video, because this doesn't ensure that we find an Eulerian path even though we know one exists. The find start node method does exactly what it sounds like. It looks for a node which is a valid starting node, meaning a node with exactly one extra outgoing edge, or in the case of an Eulerian circuit, just any node with an outgoing edge. It's important that we start at a node with an outgoing edge because our graph might contain singleton nodes that have no outgoing edges, but another component in the graph might have outgoing edges, which is where we really want to start if we are to find an Eulerian path. Next up is the depth first search method, where things get interesting. It turns out the depth first search method is really short and could even be shorter, but at the expense of readability. Remember that when calling this method, the first node is the starting node, which is the at variable in this method, which, if you haven't guessed it yet, is the current node index we're currently at. In essence, what's happening in this method is that while the current node still has unvisited edges, we're going to select the next node to explore and call the depth first search method recursively. Each time we take an edge, we decrease the number of outgoing edges for that node, which means that eventually there will be no more outgoing edges for the current node, and the loop will terminate. Once this happens, we can add the current node to the front of the solution. The key realization in this method, I think, is that you have to notice that the out array is being used as both a way of determining if there are any unvisited edges left at the current node, as well as an index for reaching into the adjacency list to grab the next node to visit. Let's go back up to the get Eulerian path method. Once we've finished executing the depth first search, the next thing to do is ensure that we've found an Eulerian path. It could be the case that the graph is disconnected into multiple components, in which case the correct thing to do is to return null, because no Eulerian path exists. Checking that the graph is disconnected is not something the graph has Eulerian path method verifies, and this is intentional because it's easier to do after running the depth first search by ensuring that the solution actually has a size equal to edge count plus 1. The next thing I do before returning the solution, which is optional, is simply to empty the contents of the linked list into a primitive integer array, just for convenience. I do this because it's easier for the caller to index an array than it is a linked list. The rest of this file are just helper methods for creating a directed graph and adding directed edges to the graph. I also provide two examples, one from the previous slides and another that I made up. I encourage you to look them over to understand how this program works. Thank you for watching. Please like this video if you learned something, and subscribe for more mathematics and computer science videos. I'll catch you next time.